This is the brief on Energy Inc.'s hybrid power applications. Okay, so we're looking at Energy Inc. It's this really innovative printable power source. What it does is actually pull electricity right out of the moisture in the air. Pretty cool, huh? And the big goal here? To tackle solar power's biggest headache. The fact that it just stops working when the sun goes down. First off, how it helps. This hydrovoltaic tech is actually designed to team up with standard solar panels, making a kind of hybrid unit. See, it provides this steady, low-power trickle charge, just using air moisture. That's key for keeping, say, off-grid batteries topped up all night long, making the whole system way more reliable. Second, the performance gains have been kind of mind-blowing. We're talking a 1,000-fold increase in power density in under 12 months. Seriously. Lab tests? They're showing density even better than some commercial solar cells. A small 64-cell setup even pumped out over a watt-hour across 3.5 days, proving it can work for integrating into smaller devices. Finally, though, there's the scaling question. Look, the design is awesome for prototypes. Easy 3D printing, custom builds, great for tinkerers. But getting this into mass-produced products we can all use, well, that totally depends on making tons of these cells reliably and affordably with automated screen printing. That's the real test. So, bottom line, the future of dependable, round-the-clock portable power really hinges on whether these next-gen moisture harvesting cells can be successfully scaled up for commercial production.
Welcome to the deep dive. Today we're digging into something potentially game-changing in energy, a source that actually pulls power from the air around us.
That's right. We're looking at whether this air power, specifically using atmospheric moisture, can realistically start competing with the big players like solar.
Yeah, especially solar, hydro, even geothermal. Our mission today is really to sift through the material and see if this is just hype or, the real deal for continuous power.
And it's a critical question because, well, almost all renewables struggle with intermittency, don't they? Maybe geothermal is the exception.
Right.
So we're focusing on these hybrid power units. They combine standard solar panels with this new stuff called Energy Inc.
Energy Inc., okay.
And the whole point is to tackle that classic 24-hour power problem.
Yeah.
The fact that solar just, stops working at night.
Okay, so the idea is this ink keeps going day and night. But how? What is it? The sources mention Australian Advanced Materials, UNSW, graphene oxide.
Exactly. It's a printable material, and the core tech is hydrovoltaic.
Hydrovoltaic. Break that down for us.
Simply put, it uses graphene oxide's unique structure to interact with water molecules in the air. As moisture gets absorbed and then released, this sort of friction, let's call it, generates a voltage.
So it literally turns humidity into electricity.
Directly into electricity, yeah. No moving parts needed, just ambient moisture.
And the numbers are what's turning heads, right?
Yeah.
I saw this figure. A prototype cell hitting 21.5 milliwatt hours per square centimeter. That sounds impressive, but how does it stack up against, say, a typical solar cell? They're usually measured in milliwatts per square centimeter, around 20 milliwatt WCMNO.
That's the key difference, and it's crucial for you to get this. Solar power is measured instantaneously. That's the milliwatts, MW, how much power it's making right now.
Okay.
Energy Inc.'s figure, the 21.5 milliwatt, that's milliwatt hours. It's the total energy collected over time, like a full day or a cycle.
Ah, I see. So because the ink works 2047, even if its instant power is lower, the total energy gathered over a whole day could actually be higher than a solar cell of the same size.
Potentially, yes, because the solar cell's output crashes to zero every single night. The ink just keeps trickling in energy.
And the speed of development here is wild. Sources say a 1,000-fold increase in power density in less than a year.
It's a massive leap, yeah. And reportedly, over 200 times better than other ways people have tried to get electricity from moisture.
But, okay, the big asterisk. Laboratory conditions. What happens out in the real world with changing humidity, temperature swings? Does it still work?
That's definitely the next hurdle. Performance does vary with conditions, no doubt. But the research suggests it still generates some continuous power across a decent range.
Which is why you need the hybrid system.
Exactly. You lean on the high-power solar during the day. That's your day mode. Then, when the sun sets, the Energy Inc. takes over for night mode, providing that continuous, albeit lower, power.
Right. Makes sense. But if you have these two different technologies, how do you actually combine them? I read something about them not liking each other.
Yeah, thermal conflict. That's the enemy here. You can't just slap the ink onto the back of the solar panel.
Why not? Seems logical.
Because solar panels get hot. And that heat dries out the Energy Inc., basically killing its ability to work with moisture.
Okay, so they need to be separate, decoupled.
Precisely. The clever designs use a separate module for the energy ink. Think of something like an accordion or bellows, a structure you can deploy.
To get more surface area.
Maximize surface area, maximize airflow around the ink. Keep it cool and let it breathe that moisture. Then both sources feed into a single charge controller and battery bank.
That sounds perfect for things like RVs, camping gear, maybe even disaster relief kits where you absolutely need power around the clock.
Definitely. For those portable off-grid uses, that extra energy yield overnight could be a total game changer.
But there's always a but, isn't there? What's the catch?
The commercial reality. It comes down to cost and availability. Right now, these energy ink cells are proprietary,
Meaning expensive and hard to get.
meaning they're basically restricted to R&D labs at the moment. The huge challenge is scaling up manufacturing reliably and affordably.
So making sure you can print square meter after square meter of this stuff consistently and building a whole supply chain, that's the roadblock.
That's the mountain they have to climb before you see this in, say, a portable power bank you can buy off the shelf.
Okay. So summing up then, the big takeaway for you listening is that this energy ink tech offers a way, potentially, to achieve real energy independence by solving solar's biggest weakness, intermittency.
That's the core vision. And maybe a final thought to leave you with. Think bigger picture. They're not just aiming for portable chargers.
Ooh.
The ambitious goal, the sort of moonshot, is to eventually have this technology generate enough power overnight, just from the moisture in the air in, say, an apartment building parking bay,
Okay.
to put a small charge into an electric vehicle.
Mm-hmm.
Enough to drive it away in the morning on power, literally pulled from thin air.
Wow. Okay.
What does that scale look like? And can they get there? That's something for you to definitely watch in the future, a real test for air power.
Let's be real. We all love solar power. It's clean. It's pretty much endless. But, it's got this one very obvious flaw. The sun goes down every single night. Well, today we're going to dive into a really fascinating new technology that's trying to solve that exact problem.
So let's just start with this one simple question that gets right to the point. What if that solar panel, the one on your roof or maybe on your RV, what if it just didn't stop working when the sun set? What if it could keep pumping out power all night long?
And this chart right here tells the whole story. You've got your typical solar curve, right? A huge spike of power during the day, and then, boom, it drops to zero. But look at that other line, the energy ink. It's this low, steady hum of power, 24/7. See, the goal isn't to replace solar at all. It's to work with it, to fill in that massive gap from dusk till dawn.
So what is this stuff? This technology that promises to work in the dark? Well, it's a completely radical new way of thinking about energy, and it all comes down to a special kind of ink.
Yeah, it's called energy ink, and it is pretty much exactly what it sounds like. You can print a power source. But here's the wild part. Instead of using sunlight, it literally pulls energy from something that's all around us, all the time. Moisture in the air. It's like it breathes in humidity and breathes out electricity.
Now, you might be thinking, this is just some cool lab experiment, but this is way past that. The team has hit some really serious milestones. They've cranked up its energy density by about 40%. They've actually hit the first watt-level output, which is a huge deal. It proves it can do real work. They even had a 64-cell array generate over a watt-hour of energy. This stuff is showing some serious potential.
Okay, so knowing what the ink can do is one thing, but figuring out how to get it to play nice with a solar panel, well, that's a whole other engineering puzzle.
The best way to think about it is like this. Solar power is a sprinter. It gives you this incredible, massive burst of power, but only for a pretty short time. Energy ink, though, it's a marathon runner. It's not fast, but it gives you a slow, steady, continuous trickle of power that just keeps going. So the question is, how do you build one system like it's the absolute best out of both?
And the solution they came up with is just incredibly clever. First, you don't just slap the ink onto the back of the solar panel. That's a terrible idea. It gets hot and it can't get any air. So you give it its own separate module, this little deployable bellows thing, to let it breathe. Second, you don't bother with 2 batteries and 2 systems. Nope, 1 battery managed by 1 smart charge controller that can handle inputs from both. And third, that controller has some really intelligent logic baked in. It knows to prioritize that powerful solar energy during the day, and then, like clockwork, it automatically switches over to the ink's trickle charge at night to keep the battery topped off. It's really elegant.
So a clever design is great on a computer screen, but it has to actually survive out in the real world, right?
And that means you've got to go from a simple 3D print to something way, way more rugged. Just look at the main case. For prototype, you might just have the two halves snapped together, with the battery held in by some flimsy little printed brackets. But for the real product, no way. You're using machine screws and these heat-set threaded inserts for rock-solid connection. It just massively boosts the durability and shock resistance.
And check out the upgrade to that unique bellows module. The prototype hinge is literally just a fragile piece of plastic filament. The production version, though, uses a proper metal rod and even has little embedded magnets to snap it shut securely. It's a huge leap in toughness for what is probably the most important moving part.
So we have a great idea. We've got a really clever design. We've even got a path to making a durable product. But there is one more piece of the puzzle, and you could argue it's the most important one of all, actually turning this into a real business that makes money.
I mean, it all sounds fantastic, doesn't it? Almost too good to be true. Which, of course, brings us to the big question. What's the catch? Where's the big roadblock in all of this?
And this chart just lays the problem out there, plain as day. Here's a rough bill of materials. You got the solar panel, the battery, the electronics. These are all known things from established markets. But then you see that one line item, the Energy Inc. cells, and it's labeled critical variable. Because it's a brand new technology, its price is a complete unknown. The entire financial success of this thing hangs on that one component.
And you don't have to take my word for it. The official commercial viability analysis puts it bluntly. It says, the project carries a high degree of risk until two things happen. You can get a reliable supply, and you can get it at a commercially viable cost. Until then, it's a brilliant but very risky idea.
So who in their right mind would take on such a massive gamble? Well, this brings us to the company that's actually behind all this, a company called Strategic Elements.
You see, Strategic Elements isn't your typical company. They call themselves a venture builder. Their whole business model is to go out and find teams of scientists with these amazing breakthrough ideas and then build entire companies around them, specifically to chase these high-risk, high-reward projects.
And the way they can do this is because they have a special registration from the Australian government as a pooled development fund. Basically, this whole structure is designed to get people to invest in risky, early-stage companies by offering them tax benefits. It is built for exactly this kind of long-shot, ambitious project.
And they've got the cash to back it up. As of their last report, the group was holding over $4.2 million in cash and term deposits. That's the money they used to fund their whole portfolio of big ideas.
But let's be clear, chasing these moonshots is incredibly expensive. This chart really shows you the financial reality of it all. They've had a net loss of over $2.5 million for the last 2 years. But here, that's not a sign of failure. That's the cost of doing deep, groundbreaking research and development. It's the price you pay when you're literally trying to invent the future.
Which brings us right to our final, lingering question. We have a brilliant solution to a problem that affects everyone. But is technical genius enough? Is it enough to overcome the huge, immense challenge of creating an entire market for a technology that has never, ever existed before? That, right there, is the multi-million-dollar question at the very heart of this whole venture.